Well, I tell you, one or two people have said that they're struggling a bit with some of these in-thinking questions, so I thought I'd go through them myself and maybe give you a hand if questions like this come up in the future. Some of the questions are a bit random, like this one is a little bit random, I have to admit. So it's asking you about something called a precipitation reaction. You will have come across this at GCSE, but maybe you will have forgotten. Precipitation is just the formation of a solid during the course of a reaction. The only solid that's a product there is that one. And so the answer for the first question is B. Question 2 is a question about ideal gases. So PV equals nRT. So asking you which will not give a straight line, assuming you've got a fixed mass of an ideal gas, so a fixed amount of an ideal gas. You expected to know, aren't you, that temperature versus volume is directly proportional, and temperature versus pressure is directly proportional. You can see that here. The volume is proportional to temperature, and pressure is proportional to temperature if everything else is kept the same. So it wasn't either of those two. Volume plotted against pressure, well, on the same side. And so if you think about that, it has to be, and it is one of the things we went through in class in detail, that pressure is proportional to 1 over volume, or inversely proportional. And that is the right answer, and I'll draw a graph of that in a second. It wasn't, I mean, D was the catch-out question maybe, because it's kind of confusing. Volume times by pressure, volume times by pressure is proportional to temperature. So you could have worked out that one too. You really should have known this relationship. It's straight from the notes. An inversely proportional relationship looks like that, so that was the answer. Question 3 is asking you about why real gases do not behave like ideal gases. Ideal gases have in theory, have no interactions between them at all. Right, so at high temperature and low pressure, you have a pretty ideal gas. But that's what we've got here. So the volume occupied by the molecules of a real gas is not negligible. Okay, so in an ideal gas, the volume of the molecules is negligible. They take up no space at all. So that is correct. That's true, that statement, because it's about do not. It's confusingly written. There are some attractive forces between the molecules of a real gas. That's not right. And the molecules of real gases collide with the walls of a container. Well, they do actually do that, so that's not a wrong one, so that's not it, so that's the right answer. It's a stinker the way that question is written. So it is 1 and 2 there. I'm not sure how well I explained that, but you have to look for things that aren't true, and these first 2 statements aren't true. Question 4, here we go. This is the kind of thing I think you're struggling with more. So question 4 is what volume of 1.25 mole per decimeter cubed hydrochloric acid is required to react with calcium carbonate. So first of all, it's worth getting your head around the equation. You expected to know that that's the formula of calcium carbonate, because I've asked you to learn that carbonate is CO3 2-, and you can look up that calcium is in group 2, so it's 2+. It's also a familiar chemical. When it reacts with HCl, so you all know what that is, and it would form calcium chloride. So carbonate and an acid react together to give a salt, and the salt is calcium chloride, CaCl2, because it's 2+, and each of these is 1-. You get CO2 plus H2O, and to balance that is that. So the key thing here is that there are 1:2 ratio. You've told you've got the concentration of 1.25 times 10 to the -3 of hydrochloric acid. It's asking you how much carbon dioxide you would get. So it would produce 227 centimeters cubed. So this is the volume of the gas now. It's the volume of the solution. Volume of the gas in centimeters cubed is 227 centimeters cubed. And remember, we learned that 1 mole of gas at standard temperature and pressure, which is 0 degrees C or 273 Kelvin, is 22.7 deciliters cubed. Okay, so you can work out, you can do it without a calculator, you can do it with a calculator, you can work out quite straightforwardly 227 divided by 22700 is 0.01 moles. Okay, so the whole point is here is we work out the number of moles every time, isn't it? So we've got 0.01 moles of gas. That's what it's asking us about. So the trick is with any of the calculation questions you're struggling with is what's the number of moles you're working with. Okay, so the number of moles here is 0.01. So we need 0.02 of this stuff because we've got a balanced equation there. So 0.02. And so what volume do we need? We've got to do the volume of the solution and the concentration of the solution. So number of moles is equal to V times C over 1,000. Or if we rearrange that, I haven't got space down here to write it, so I'll just rewrite it over here. The volume is equal to the number of moles times 1,000 divided by the concentration. So you plug those numbers in. Hopefully we've got this right. So if I 0.02 times 1,000 divided by the concentration, which is 1.25, gives me 16, which is one of the answers, thankfully, which is the right answer. Okay, that's that one. So work out the number of moles of the things that you can work out the number of moles of, and then it's easy. But you've got to get balanced equations right first, and that's one of the reasons that question is a bit harder than some. Question 5. You're told that a gaseous hydrocarbon is combusted in 1,000 centimetres cubed of oxygen. 1 second.